Okay. Hello, this is Michael Hackathorn. This is my discrete structures homework 2. I'll just get right into it. So section 3.1 is what we started with. So we're going to describe an algorithm that takes as an input of in integers and finds the location of the last integer in a list, or returns 0. Now if there's no even integers in the list. So a little bit of like a summary. It's basically we're just making an algorithm that finds if the last integer was even. That's pretty much it. So some of the resources I used the book to help me. I learned the resources to do this problem through the book, and I also I believe that we did this problem together in class. So I used that to also help me do this problem. I'm going to personally I'm going to assume that the problem is going to start at 0, not like 1 or like negative or anything. So it's going to start at 0. So k equals 0 for I equals 1 to n. Now if I is even, then k equals I, and then you just return k. That's pretty much to see the uh, if the integer is even. Okay. Now, honestly, I forgot to bold this. But so justification. Now I'm pretty sure this is correct because I think we did this exact problem in class, so I'm pretty confident that this was the correct answer. In that's pretty much why I think it is. Okay, if we want to go to number 8, it's basically the same question. It's just like if there's no even integers, it's like the only difference. So it's just like find the largest integer in the list of numbers. So it's you basically just we're just gonna find the largest integer, largest even integer here. I use the book, and I'm with this problem. I used the book to help me, and I also am pretty sure we did this problem in class, so that is also a reference. I'm going to assume that a negative number can still be even. So we're going to like max is negative infinity. It's kind of hard to see the infinity, but it's fine. K equals 0 for I in. If is equals even, then list I. Now if list I is greater than max, then k equals I, then max equals list I, return k. Basically just saying that if it's greater than we're just gonna be returning k. A justification. Now we did this in class on Tuesday, so I'm pretty sure. At least I hope we all did it right during class. So that is my justification on why it's right. Number 9, we're going to be making a palindrome. So we basically see if a string of characters is a palindrome. So like the sentence is just this question is asked for me to make an algorithm that if a name or a word is a palindrome, like I don't know, like race car, and then if I did that, it would be like yes, this is a palindrome. So I used the book, and then I'm pretty sure we also um, I used like the other problems to kind of help me out, and I think we also went through this one because I remember we talked about palindromes during class. So brief assumption. I'm just going to assume that all the names that are like inputted are actually palindromes and not just like something random that isn't a palindrome. So like answer equals true. Now for check in, 1, or like in divided by 2, or in minus 1 divided by 2. Now if a sub check, equals a in minus check plus 1, answer true, else, answer false. So if it's true, then it'll be, yeah, this is a palindrome, else, false, it's not going to be a palindrome. So another justification is I'm pretty sure we did this question. I think we did multiple of these questions during class, so I think this is going to, like, that's a justification for a lot of my answers because we did them during class together. So now we're on section 3.2. 7, we're going to find the least integer in such that, f of x is big notation, or big O notation, x in for each of these functions. These are the functions right here. I'm honestly going to put a, well, there we go. So the problem just wants me to find the least integer in the given function. I use the book and then prior lessons that we did on the subject, basically, for these problems. Now I'm going to assume that the work that we did in class on Tuesday and Thursday to be correct. So I'm going to say that whenever we did this in class that this is like we did it correctly. So a n equals 3 right there, to the third, n equals 3, n equals 1, and then n equals 0 for d. Now, I believe that my answer is right because during class on Tuesday we did do this question together, so that's a big justification on why I think it's right. Um, and the 8 is the exact same question as number 7, like I say in the sentence of the summary. I used the book and like prior problems like this one, and pretty much like that and prior lessons in the book and stuff that to kind of help me out with this problem. I'm going to assume that if I did the same thing that we did for problem 7, that it's probably going to be the exact same for problem 8. So I'm going to assume that. So A is n equals 3, B n equals 5, C n equals 0, and D n equals 1. I believe that this answer is correct because if I did this problem the same that we did on problem 7, then I believe that I didn't change anything, so this should be correct. I could be wrong though. And then 9, so this it's basically just seeing if x to the third is or isn't the same as this equation. Wait, I didn't mean to put x to the 33rd. That would not be good. But to see if this with x third. So I used the book for this one because this one was honestly kind of like really difficult because I really didn't know like kind of where to start. Let me go capitalize this I. I'm going to assume that the problem that the book answered like in the back of the book is correct because like since I was having so much trouble that I really needed to use the back of the book to help me. So basically this is saying that like if x to the third did equal this, then like if you would like derived the equation, basically you would get this, which would imply that x would be greater than 3c, which is impossible, which would mean that x to the third cannot equal big O notation x squared plus 4x plus 17 in this sense. I believe this is correct. I mean, I used the back of the book to help me. Oh, I got another. I needed a comma there, it seems. But yeah, I was just I was having trouble, so I used the back of the book to help me with this one, and it helped me out a lot, and it saved me a lot of time, which was nice. Now we're on 3.3, so we got to pick only 2 of these parts for them. So on 15, so it's like what is the largest n for which you can solve within 1 second of a problem using basically this algorithm. So this question is pretty much just asking like a function of n that would be a bit like if the bit operation was 10 to the negative 19th. I used the book and then the problems we did together to help me with these problems. I'm going to assume that these problems are correct because I'm pretty sure we did both of these in class on Tuesday. So I put A is n equals negative 9, and then B is 10 to the 9th. Oh, I need to. What? It didn't even change anything, I don't think. Okay. And then the justification for the answers, I'm pretty sure this question is correct because we did these questions on Tuesday. So we did them together, so I hope that they are right. So this one is pretty much the same as 15, except it's a different like time. Instead of it being what was it, 10 to the negative 19th, this is 10 to the 11th. So I have a equals. So this question is asking me to do 10 to the negative 11th. I used the book, the work we did in class together, and then like the previous problem to help me know if I got this one for sure. I'm going to assume that if I did the questions just like we did them in class on Tuesday, that they would be correct. So A is n equals 864 times 10 to the 10th, and then n equals 9.38 times 10 to the 7th. I believe that this is correct because I did pretty much the same thing on the previous problems that we did in class on this one, so I think they both should be correct. And then 17 is basically the exact same as the other two, but it's just a different time once again. This one's 10 to the negative 12th. I used the book and then the work that we did on the other two problems. to help me on this one, and so I'm pretty much going to assume that if I did the other two questions right, and that um, these two answers should also be right. So for n to the second, log n, it's going to be n equals 7.7 to the sixth, and then 13.7 times 10 to the seventh is my idea of what these is. And then I believe that um, my answer is correct because since I did these problems just like the other two problems, nothing should be different other than like maybe different or nothing other than like different starting values like of the time. So if I did the other problems correctly, then I feel like these on this problem I should have also done correct. And I believe that is the last problem from 17 was the last problem. So so thank you for watching.